Alright guys, so again, my delta H is just the enthalpy of the products minus the enthalpy of the reactants. So we just said this, that delta H is called the enthalpy of reaction, and that's because I just want to see what's happening. I want to see the change in enthalpy or heat flow of that reaction. And since I'm really just thinking about heat flow, I could also call it heat of reaction. So in this case, we can give a numerical value for the heat of the reaction, but just as long as we know that which reaction we're involved with. So let's say, for example, we have hydrogen and oxygen, and they're going to form water. When I have hydrogen and oxygen gas, they're going to come together in a very violent reaction. So here's my hydrogen and oxygen gas molecules. They're coming together and they're going to form water. So in this case, what I see on the macroscopic scale is that there's flame, there's an explosion, and those are really big indicators that the system has released energy to the surroundings. So in that case, my delta H would have a negative value. So this would be considered an exothermic reaction. Okay? So if they have a negative value, then that means if I look here on my energy diagram, my initial state must have had a higher energy than my final state. And I can see that too. Okay, we have a couple just like little quick guidelines when we're talking about enthalpy because we're going to get into writing these thermochemical equations and reactions. So it's really important that we understand these things. So it says the following guidelines are helpful when using thermochemical equations and enthalpy diagrams. So our enthalpy diagram is very similar here to like our energy diagram. So instead of internal energy, I'm just calling this enthalpy. Okay, number one, enthalpy is an extensive property. So enthalpy is an extensive property. The magnitude of my change in enthalpy is just going to be proportional to the amount of reactant that's consumed in the process. So what I mean by that is in my enthalpy diagram here, I have CH4 plus 2O2 will yield CO2 plus 2 water molecules. So right now, if I'm going to burn 1 mole of methane gas to get my combustion reaction here. And if I do that, if I combust 1 mole of methane gas, then it could release 890 kilojoules of heat. So I could get a change in enthalpy of a negative 890 kilojoules. Let's say, though, that I had 2 moles of methane gas. If I have 2 moles of methane gas, then that means that I'm going to have twice as much heat flow. I'm going to have twice as much of that change in enthalpy. So if I had 2 moles of methane gas and that 4 moles of oxygen, so we're just going to make sure that it's balanced then correctly if I had 2 moles of this. So I have 2 moles of methane gas. My delta H would no longer be a negative 890 kilojoules. It would actually be negative 1780 kilojoules. So I'm just going to double that. So if I double one of my reactants, then my change in enthalpy will also double. If I quadruple one of my reactants here, if I'm quadrupling my methane, and that's what I'm looking at, then my enthalpy change can quadruple. Number 2, delta H, my change in enthalpy for a reaction in the forward direction, is equal in size but has an opposite sign for the delta H for the reverse reaction. So if this was my reactants, I had methane gas reacting with oxygen, and my final state would be carbon dioxide and water, I could see that this would be an exothermic process. So my initial state has a higher energy than my final state. So I would have that negative enthalpy change. But let's say that we started with carbon dioxide and water, and then my products, maybe from this, I could react those two to get methane gas and oxygen. And in that case, I would need to absorb energy for this reaction to take place. So if that happens, if I just have the exact opposite reaction that would occur, it would be a positive 890 kilojoules. So if I'm thinking about reverse reactions, they're just going to be equal in magnitude but opposite in sign. So if I'm moving from reactants to products, in this case I'd have this negative 890. If I went the reverse way and did from products to reactants here, it would be a positive 890 kilojoules. Number 3 is that the change in enthalpy for a reaction will depend on the state of the products and the state of the reactants. So in this case, I produced liquid water, but I could also have produced water in the form of gas. And if I had produced water in the form of gas, I would have had a different change in enthalpy here. So states of matter are also really important. And we're going to see that more when we do Hess's law and some more delta H reactions. So right now, I just want us to know that we really need to pay attention to the state of matter for products and reactants. Okay, so let's look at this next question. This says, how much heat is released when 4.50 grams of methane gas is burned in a constant pressure system? And I gave you the formula here. So we have methane gas, and that methane gas is reacting with oxygen to produce CO2 and water. Okay, so how would I do this? Okay. So how much heat is released when 4.50 grams? Let's go ahead and let me write our reaction out again. So I had CH4, that was gas, plus 2 O2 gas is going to produce for us CO2 gas. I want to make sure that doesn't go off the board. CO2 gas and 2 H2O, my liquid water. Okay. So I also gave you, at the end of that, a change in enthalpy, and that change in enthalpy is equal to a negative 890 kilojoules. Yep, kilojoules. When we write a reaction this way, I write out the reaction that's happening, and then I write the change in enthalpy after that. That's something that's called a thermochemical equation. So when we indicate what's happening in the reaction, which we did here, and the change in enthalpy with the sign, the magnitude, and the unit, I see I have a thermochemical equation, just so we throw out that vocab word too. Okay, so they're asking us, I'm starting off with 4.50 grams of methane. That's what I have. I want to know right now how much heat can I release if I started off with 4.5 grams of methane. Well, I need to know how many moles that is, because I know, looking at this equation, 1 mole of methane can produce a change in enthalpy of negative 890 kilojoules. But I need to figure out what my delta H will be if I'm starting off with 4.50 grams of methane. So if in this reaction I'm looking at moles, not grams, I'm going to need to convert this grams of methane into moles of methane. So let's go ahead and do that. So I have 4.50 grams of methane. I want to convert that to moles of CH4. And if I want grams down here below, what am I going to have to use? We are going to have to use our fantastic periodic table. Here we go. And I would get here for my mass 16.0. So if I did 4.5 divided by 16, I'm going to get 0.281 moles of CH4. Okay, so right now I know 1 mole of CH4 can have a heat change of or produce a heat of negative 890 kilojoules. But I want to know, what's my change in enthalpy going to be if I have 0.281 moles of CH4? So if I have 0.281 moles of CH4, and I want to find kilojoules, I know that in 1 mole of CH4, we can produce a negative 890 kilojoules of heat. So now my moles of CH4 will cancel. So if I did 0.281 times a negative 890, we would get a negative 250 kilojoules. There we go. Okay, we have one more on here, and I would like to do that one as well. So let's do that one. Okay, hydrogen peroxide can decompose to water and oxygen. Calculate the quantity of heat released if I have 5 grams of hydrogen peroxide decomposing at constant pressure. So I gave our thermochemical equation here. We have hydrogen peroxide decomposing to water and oxygen. I have my change in enthalpy, which is a negative 196 kilojoules. So let's go ahead and do that one. So we had 2H2O2. Liquid is going to produce liquid water and oxygen gas. And my delta H was a negative 196 kilojoules. Okay, and we were wondering if I started off with 5 grams of hydrogen peroxide, what would my change in enthalpy be then if I had 5 grams? So I have grams, and I know that 2 moles of hydrogen peroxide for this reaction, or in this reaction, is going to make my negative 196 kilojoules. So I need to figure out, though, these 5 grams of H2O2. So let's convert grams of hydrogen peroxide to moles of hydrogen peroxide. So 1 mole of H2O2 over grams of H2O2. And if I found my molar mass, I would know that would be 34.0. And so if I take 5 and divide that by 34, that's going to give me 0.147 moles of H2O2. Okay, so now I know my moles, and now I can compare how many moles that I have in the reaction with my delta H. So I had 0.147 moles of H2O2, and I know that there's negative 196 kilojoules of energy that will be released in this reaction for every how many moles of hydrogen peroxide. How many moles do I have in this reaction? There are 2. So I have to write for every 2 moles. So coefficients are super important here. So if I want to know how many moles of hydrogen peroxide, if I'm starting off with 5 grams, or if I'm starting off with 5 grams, what my delta H would be, I need to make sure that I look at that coefficient for hydrogen peroxide, because I got a change in enthalpy of negative 196 kilojoules with 2 moles of hydrogen peroxide. So I need to make sure I have that 2 there. So if I did my 0.147 times a negative 196 and then divide that by 2, you should get a negative 14.4 kilojoules. Okay, so let's keep moving. All right, guys, so we are going to get into something that's called calorimetry. And since we can't know the exact enthalpy of the reactants and of the products, we just measure delta H kind of indirectly, and that's through something called calorimetry. And calorimetry is just the way that we can measure heat flow. The picture that's shown here is just a device that we use to measure heat flow, and this setup is called a calorimeter. So this is called a calorimeter. Pretty much how this works, we are going to add two aqueous solutions, so let's say those would be my two reactants, to this little coffee cup calorimeter. So I have two little styrofoam cups here that are nested inside one another, and I've got a cork stopper to kind of like block anything else from coming into. So I'm really just trying to contain the surroundings that are in here. I don't want anything else coming in from the outside. I have a glass stirrer in here and a thermometer. That thermometer can calculate or find, not calculate, but it can measure that change in temperature for us. And so if I add my two aqueous solutions in here, if I'm adding my reaction mixture, once the reactants mix, they can form products. In this case, in a calorimeter, there is no physical boundary, really, between the system and the surroundings. So the reactants and the products of the reaction are what we are going to call the system. The reactants and the products of the reaction are the system in a calorimeter. And the water in which they're dissolved in is going to be considered the surroundings. Okay, so reactants and products of the reaction are the system, and the water is what we're going to call the surroundings. So if our calorimeter is perfectly insulated, then any heat that's released or absorbed by the reaction is going to change the temperature of the water, right? So if I have a perfectly insulated calorimeter, any heat that's released or absorbed by the reaction is going to change that temperature somehow. So we can measure temperature change of the solution, and we can think about what's happening then in the reaction. So for an exothermic reaction, heat is lost by the reaction and gained by the water. So actually, let's write these down. Let's write these little notes down. Okay, so for an exothermic reaction, heat is lost by the reaction and gained by the water, by the surroundings. So heat is lost by the reaction and it's gained by the water. So if the water is gaining that energy, what do you think is going to happen to the temperature? That temperature is going to increase. That temperature is going to go up. So if I see in my calorimeter, if I look at that thermometer and I see that the temperature is increasing, I know that that reaction is losing heat and the water, the surroundings, is gaining that energy, and that's what's making my temperature increase. If it were an endothermic reaction, it's just going to be the opposite. So if this were endothermic, heat is going to be gained in that reaction is going to gain heat, it's going to gain energy, so the water must have lost that energy. So in that case, if my water is supplying energy to the reaction, my temperature wouldn't increase, my temperature would actually go down. My temperature would decrease, okay? So the heat gained or lost by the solution is really equal in magnitude but opposite in sign to the heat that's being absorbed or released by the reaction. So let's go back. Okay, I'm going to go back to this. Oh man, I thought that was for my next slide. Okay, well, just kidding. Let's go back. Here. So we were saying that the amount of heat that's gained by the reaction or lost by, the heat that's gained or lost by the solution is going to be equal in magnitude but opposite in sign of what's absorbed by the reaction. Okay? So I want to say the heat of the solution is equal in magnitude to the amount of heat of the reaction. So the energy between these two, if water is giving energy to the reaction, then that water has lost a certain amount of energy, which means that the reaction is going to gain that same magnitude of energy. So if the solution gave it 20 kilojoules of energy, the reaction then gained 20 kilojoules of energy. That's what it's saying. But it's opposite in sign. So if this one's positive, my Q reaction is going to be negative. So they're equal in magnitude but opposite in sign. So Q solution could equal a negative Q reaction, or it could be vice versa. A negative Q solution would equal a positive Q reaction. Okay. We need to define just one more thing, and that's called heat capacity and specific heat. So for heat capacity, we know that all substances will change temperature when they are heated, but the magnitude of the temperature change produced by a given quantity of heat can vary from substance to substance. So all substances, again, will change temperature when they're heated, but how much temperature change we actually get, or how much temperature change is produced, is going to vary based on what substance that I have. So because of that, we also need to think about something called heat capacity. The greater the heat capacity, the greater the heat required to produce a certain amount of temperature. We also have something that's called specific heat capacity. And specific heat capacity is the amount of energy required to raise the temperature of 1 gram of a substance by 1 Kelvin, or we can think of 1 degree Celsius. And some of these specific heats was on the table on this previous slide here. So specific heat of substances. So I have nitrogen gas, aluminum, iron, mercury. So these specific heats will always be given to you. It's something that scientists have calculated for particular substances. So we've already done the calculation here. We're just going to use these numbers if we're thinking about them in terms of a reaction. The one that you should know pretty much off the top of your head. Liquid water has a specific heat of 4.18 joules per gram Kelvin. So specific heat has the units joules per gram Kelvin. Joules per gram Kelvin. And water, liquid water, that's super important. Liquid water is 4.18 joules per gram Kelvin. Okay, so, and again, specific heat, it says specific heat capacity, but we really just call it specific heat. It's the amount of energy required to raise the temperature of 1 gram of a substance by 1 degree, by 1 Kelvin or by 1 degree Celsius. So we can calculate specific heat, or we have calculated specific heat in the past. And that is, specific heat is equal to the heat transferred over mass times temperature change. So I do not want you to call this S. I think that it's some commonplace to call it S. I prefer you call this C. So in your notes, change this S to a C. This should be C. C equals Q over M times delta T. C standing for specific heat, Q standing for heat, mass M standing for mass, temperature change, I'd have to have delta T. So C equals Q over M times delta T. Okay, and that brings us to one of these questions. This says, how much heat is needed to warm 250 grams of water from 22 degrees Celsius to 98 degrees Celsius? Okay, so again, that says how much heat is needed to warm 250 grams of water from 22 degrees Celsius. So initially it was 22 degrees Celsius, and then it went to 98 degrees Celsius. So we moved from 250 grams of water and 22 degrees Celsius to 98 degrees Celsius, and I want to know how much heat. So I'm looking for Q. I am looking for Q. I know from my previous table with the specific heats liquid water has a specific heat of 4.18 joules per gram Kelvin. So I'm going to write that. My C equals 4.18 joules per gram Kelvin. And we just said C equals Q over M times delta T. But I want Q. I don't want C because I already have C. And I have my temperatures here, and I have my mass here. So I'm going to rearrange this equation here to just have it Q equals. I want to rearrange to solve for Q. So if I did that, I would get Q equals M times C times delta T. And I remember this formula not this way, but this way, because this would be Q equals MCAT. If I think about this as like being a little a. So Q equals MCAT. Heat is equal to mass times specific heat times the change in temperature. So now, all I really need to do is plug these numbers in here. But, one thing, specific heat is here in Kelvin, but up here, we measured it in Celsius. But since this is change in temperature, it's change in, the Celsius and Kelvin scale really would have the same changes in temperature. So if I did my 98, my final, minus my initial, if I did 98 minus 22, I'm going to get a change, my delta T would equal 76 degrees Celsius if I left it in Celsius, right? And let's say I converted the 22 and the 98 to Kelvin. Let's just see. So if I did 22 plus 273, I would have got 295 Kelvin. And if I did 98 plus 273, I would have got 371 Kelvin. If I subtracted my final minus my initial, so if I subtracted 371 minus 295, that would have given me 76 Kelvin. So because the scale is pretty much the same, they're just starting off at different places, I can say that the change in temperature, whatever I find for the change in temperature, it's going to be the same regardless if it's Celsius or Kelvin. But make sure on your AP test that we want to make sure that in there are units for temperature. You may have found 76 degrees Celsius, but then I would want to write that's equal to 76 Kelvin, okay? So now let's plug this stuff in. So Q equals mass, which is 250 grams. This stays grams because my specific heat unit has grams here. So that's why we're not converting that to kilograms. So I have 250 grams times C, which was 4.18 joules per gram Kelvin, times change in temperature, which will be 76 Kelvin. And if I multiply all those together, we are going to get a heat of 7.6 times 10 to the 4th. That would be joules. 7.6 times 10 to the 4th joules. Okay guys, so this is actually where I want to stop. So we actually only went from slide 30 to 40, but I think the video is long enough for you to watch. So if you have questions on anything, let me know. I am also going to post, like I said, I'm going to post this pre-lab questions. And it'll be homework for Monday, so you don't have to do it over the weekend. But if you don't want that homework on Monday, then you can just go ahead and get it done over the weekend. So I will see everyone Monday, and have a really great weekend. Bye, guys.